by the Climate Variability and Predictability Program of NOAA's Climate Program Office. These webinars are intended to showcase the research funded by the Climate Variability and Predictability Program that was conducted as part of the DYNAMO field campaign, which ran from the fall of 2011 to the spring of 2012 in the Indian Ocean. This field campaign, consisting of in situ observations from moorings, aircraft, land, and shipboard sensors, is part of a larger research program involving data analysis, modeling, and forecast improvement components that are ongoing today. The overarching goal of DYNAMO is to develop a better understanding of the Madden-Julian oscillation because it is an important influence on the global climate system, especially on seasonal to interannual scale. Advances in our understanding of the MJO can improve prediction skill in climate and weather models, allowing them to provide better forecasts and projections in the future. In pursuit of this goal, DYNAMO tried to capture the structure and evolution of cloud populations, air-sea interactions, and larger-scale environmental interactions related to the MJO. This series of presentations will share the latest results from these projects and will allow the PIs to discuss the importance of their work, outcomes, and lessons learned to date with a broader scientific community. As you listen to the presentations, if you have a question you would like to ask the presenter, please type it into the question box, which is on the control panel for GoToWebinar and will probably be on the right side of your screen. You can enter these questions at any time, and we will address them at the end of the presentations. Please include your name, who you are addressing the question to, and your question, because of the number of people listening to the presentation, all of your lines will be muted, which is why we have to use this question box instead. So, our first speaker today is Wanqiu Wang with a talk entitled Application of DYNAMO AMIE Observations to Validate and Improve the Representation of MJO Initiation and Propagation in the NCEP CFSv2. He is a meteorologist at NOAA's National Centers for Environmental Prediction, Climate Prediction Center, where his work focuses on assessment and documentation of the CFS model, as well as processing it for the consolidation of seasonal outlooks. On this project, he has been working in collaboration with Joshua Fu of the University of Hawaii. Wanqiu, thank you for joining us, and at this time we will turn the controls over to you.
Thank you. Good afternoon. I'm very happy to have this opportunity to report our work on MJO prediction for the DYNAMO field campaign period. My name is Wanqiu. Joshua has a schedule conflict with this webinar and was not able to come to present the results. So the ultimate goal of this project is to improve prediction skill of Madden-Julian oscillation in NCEP climate forecast model, CFSv2. In this project, we carried out a number of tasks which will be summarized in this talk. We will briefly give an analysis of MJO observed during DYNAMO period. We will review operational forecast. We will assess the capability of CFS, GFS, and the University of Hawaii model. And we will assess the impact of air-sea coupling on MJO forecasting. And we will also discuss experiments for cumulus parameterization and SST uncertainty. And at the end, we will also show that MJO can be categorized into two types, coupled and uncoupled. So they observed MJO during the DYNAMO period. From September 2011 to March 2012, there were 5 MJO events. Overall, all these MJO events are associated with leading warm SST anomalies. In particular, we see that the November MJO and March MJO are associated with most robust coherent SST anomalies. And I want to mention that October and November MJO are primary MJO, and September MJO is, October and November are successive MJOs, and September is primary MJO. So thanks to John Gottschalk's team at CPC, they provided the operational forecast from 7 operational models. This allows us to examine the current issues in the operational model. Here I'm showing the forecast for October and November MGO events in top panels, and for September event in the lower panel. The October and November events are successive events, and the forecasts are pretty good. Here, the black line is observation, which is difficult to see, which is good. That means model forecast and observation are basically mixed together for both events. For the primary case, the forecast is not very good. We have forecasts at 1 week lead and 2 weeks lead. So even for 1 week lead, the forecast did not reproduce observed intensification and propagation. So for the primary case, the forecast is not good. So the prediction is case dependent. Also, given this collection of observation and operational forecasts, we identified a few common issues across all operational models. Here we listed three major issues. The top panel shows the slow propagation. Basically, the observed is a black line here. Basically, the all forecast propagate more slowly compared to observation. And the second issue is all models have difficulties to propagate across maritime continent. So basically, when approaching the continent, the MGO propagation stopped there. And the third issue is the forecast. Most of the forecasts are weaker than the observation. So the magnitude is weaker compared to the observed. This is also the third major issue. Now, looking at the forecasts, now we focus on forecasts from three models: the NCEP GFS, CFS, and University of Hawaii model. Now, this is a forecast from November 4th, which was about 2 weeks before the onset of this initiation of this MGO event. We see that here we are looking at ORR anomaly. The observation is plotted with shading, and the forecast is contours. So the best forecast, if a forecast is good, we would see the shading and the contours overlap. And we see that both models, the upper panel is CFS, the lower panel is University of Hawaii model, and both models predict the initiation of this MGO event, which is very good. And the propagation, the CFS version 2 appear to propagate more slowly compared to observation, and Hawaii model propagation appears to be somewhat better. So there was an email sent from Joshua to his colleagues, Owen and Hisayuki, who are actually on the Reveal taking the observation at that time. And the email warned them that the MGO is coming in 2 weeks, which turns out to be a very good forecast. This is another forecast from initially from 18th, which basically is similar. The major issue now is, again, the model propagation is slower compared to observed. And we also validate the forecast against observation in the surface heat flux. Here we were showing solar radiation in the top panel and latent heat in the lower panel, which is this is the heat flux averaged at the equator around 80 degrees east. Basically, we have a forecast for the red line is forecast of average for the first 10-day lead time, and the blue is the day 11 to 20, day 20 lead time, and black is observation. And what we want to show here is that for the first 10-day lead time, the model prediction is quite reasonable. Occasionally, it lags observed by a couple of days. But when the lead time increases, the forecast lags observation by several days, which is consistent with the other quantities we have shown. So to summarize the forecast, we calculate the correlation scale of MGO index. Here we have three pair of curves: GFS in red, and CFS green, and the universal Hawaii model in black. Taking 0.5 as the to represent the useful forecast, we see that the GFS is skillful only through 13 days, and CFS is green, universal Hawaii model, or around 25 days or 28 days. When we put two models together, universal Hawaii model and the CFS, we have a much better forecast, which is about 36 days. So that means the multi-model ensemble does help. And the major thing is that we see the difference between GFS and the other two models, which is about 10 days. We also analyze the forecast based on CFS handcast. I want to quickly show you some results from that. So this analysis is based on 12 years handcast. Here is a composite of MGO index from each initial phase. The left panel is for phases 1, 3, 5, 7, and the right panel is for phases 2, 4, 6, 8. We can see all three major issues which we saw in the operational model. First, the propagation. The blue lines are observation, and the red dashed line is a forecast. We see that for almost all forecasts, for all initial phase, the forecast is behind the observation. So that means the forecast the forecast is slower. And we also see that the amplitude in the forecast gets weaker and weaker compared to observation. And if you look at the forecast from, say, phase 3 and phase 2, we see that the model was unable to has difficulty to propagate across the maritime continent. So that's all three. So we can see all three major issues in the model. Okay. So now I will skip this. Now we talk about another interesting thing. During the intensive observation period, we see a cyclone genesis around November 26th. This TC was named TC05A, or Thanksgiving TC. We want to look how good the model performs in predicting this MGO event, as well as this tropical cyclone genesis. First, we look at the MGO index from November 11th. The observation shows propagation from phase 7 from phase 7 to phase 2 within 2 weeks or so, and continue to propagate across the maritime continent. Both CFS, which is blue, and the universal Hawaii model, which is red, propagate similarly with observation, so which is good. And GFS produced a intensification within 2 weeks, but failed to generate the propagation into Western Indian Ocean. So looking at spatial maps, we are looking at the OLR anomaly, which is color, which is shading, and 850 millibar winds, which are contours. These are the forecasts at about 2 weeks lead time from November 11th. So we see that the observation shows that the well-developed convection in the Indian Ocean with corresponding strong westerlies near the equator. This pattern was well captured in CFS version 2 and the universal Hawaii model. although the CFS underestimated the convection intensity, and University of Hawaii model produced weaker westerlies. And both models forecast the cyclone in Indian Ocean. The GFS at week 2 basically missed all MGO signals and did not generate this TC genesis. I'll skip this. So the question is, what caused the dramatic difference between GFS and the other two models? We can attribute the difference to two things, basically, major possible causes. One is ASC coupling, and the other is model physics. And because GFS is an uncoupled model, and the other two are coupled. So to address this question, we carried out experiments to understand the impact of ASC coupling. And we carry out 4 experiments with the University of Hawaii model. The first one is CPL, which is a standard coupled model. And the other 4 are atmosphere-only models. FSST, forecast SST, is the forecast with the same atmospheric component of the same model, but forced with SST from CPL. And PERSST is the forecast with the initial SST persisted throughout the forecast. And the fourth one is forced with observed TMSST. And here's a comparison of the scale in terms of correlation of MGO index. We see that with persistent SST, which is blue, the model scale is skillful at about 19 days. And for coupled model, which is red, and the forecast with SST from coupled model is about 28 days or so. So the coupling extends the forecast by 1 week or so. And with observed SST, which is TMI, which is black here, we see that the forecast scale is skillful through longer than 40 days. So which means if the model can generate the realistic SST, the forecast can be very good. So there's a lot of potential to explore. And we also look at the dependence on convection parameterization and SST uncertainty. So I will show you why we want to look at SST uncertainty too. Here, the experiments were carried out with NCEP GFS, atmosphere-only model, which is the atmospheric component of CFS. And we use the 3 SSTs, climatology, NCDC analysis, and the TMI. And we also 3 convection schemes, the SAS, which is CFS convection, SAS2, which is a modified SAS, which is a newer version of SAS, which is used in GFS. And we also tested another convection scheme, which is a relaxed or covered Schubert scheme. Okay, the experiments were initialized from CFSR and 30-day targeted days, and this is for DYNAMO period. So now here we compare observation with the forecast with SS2 and size and rise with climatological SST. So without any SST information, we see that the GFS convection scheme basically is weak, very weak compared to observation. With SAS scheme, the forecast anomalies is stronger. And if we use RAS scheme, the forecast is pretty good for October MGO and for December MGO. But the model forecast for November even is quite weak. And we see the similar contrast comparison among the convection schemes with TMI SST. But overall, the overall scale is much better now with a more realistic SST. In particular, November forecast becomes really, really good with RAS scheme. So I also have the quantitative comparison for this 3 SST and 3 convex schemes. Basically, we do need SST, which is blue, good SST to give a good prediction. We also need the convex scheme is also need to be tuned. And the RAS scheme appear to be better than the other 2 schemes, SAS and SAS2. And so what can we do to improve MGO? So based on this experiment, we can we suggest that to improve MGO prediction, we can replace the current CFS convex scheme with RAS and improve SST accuracy to have better intrasignal oscillation in the signal and diurnal variability. For GFS, we can use we can use RAS scheme and also use SST, specify SST from a couple model instead of persisting initial anomaly. So one more thing I want to talk about is a categorization of MGO types. We want to show that the MGO can be grouped into 2 groups, coupled versus uncoupled. So we analyze the impact of various coupling by comparing forecasts from different different runs. Here we have several curves here, but the main thing is we want to compare the run, which is green, which is forecast with persisting initial anomalies. That means there's basically no realistic SST for this forecast. And the other runs, which is the red is like a standard coupled run, and blue is atmosphere only run using SST from the red, from couple model. And the purple is forecast with observed SST. We will compare that with observation, which is in black. So we want to the message here we want to show is that sorry, I'm trying to get rid of this. For October case, the forecast is good, even without interactive SST or without any realistic SST. And for November case, the forecast without the realistic SST failed to generate the propagation of the observed in observation, where other forecasts with with coupled model or with observed SST, they generate this forecast very nicely. This is based on University of Hawaii model. We can see the same thing when GFS is used. Here we compare observation on the left panel with the forecast experiments using the RAS convex scheme. The middle panel is using climatologic SST. The red panel use observed TMI SST. So we see that for October case and for December case, the forecast with climatologic SST look quite reasonable compared to the forecast with observed SST. And for November, the forecast without realistic SST is much worse compared to the one with observed SST. So interactive ocean is it does matter, but it's case dependent. So here's a summary. We found that 2 of the observed MGO during DYNAMO period have robust, coherent, positive SST anomalies leading to MGO convections, and for other cases, SST anomalies are weak. And the initiation of successive MGO is more predictable than primary MGO. And the major issues in the forecast is slow propagation and the maritime continent barrier and weak intensity. During the DYNAMO period, MGO forecast skill for GFS, CFS, and the University of Hawaii model is 13, 25, and 20 days. and GFS is needs to be improved. And ASC coupling is important, and it extends the forecast by 1 week to 10 days. The interactions between the November MGO and the Thanksgiving was well predicted by UH model and CFS, but not by GFS. And CFS MGO forecast may be improved with alternative cumulus parameterization and more accurate SST prediction. GFS forecasting can be improved with another convention scheme and with SST from CFS, or we can couple GFS to a mixed ocean model. And we also found that the MGO AS interaction impact is case dependent. The MGO can be categorized into coupled and uncoupled types. That's it. Thank you.
Thank you, Wanqiu. That was great. And I'd like to remind everybody that if you have questions, go ahead and enter them into the question box, which is probably on the right side of your screen on the control panel, and we'll take those at the end of the next presentation. And so with that, we'll move on to the next presentation. Up next is Guang Zhang. He's presenting on global model investigation of MJO initiation for DYNAMO. And he's currently at the Center for Atmospheric Sciences at Scripps, and his research interests include climate modeling, convection and cloud parameterization, atmosphere-ocean interactions, and the convective transport of momentum. Guang, welcome, and we'll turn the controls over to you now.
Okay, thank you. Can you hear me now?
Yes,
Hello?
you're good. You're good to go.
Okay. All right. So we've been trying to look at the global model simulations or hindcast of MJO initiation for the DYNAMO period, and we got a publication earlier this year. And so the objectives of our work is to investigate the MJO initiation in the Indian Ocean using the NCAR CAM3 and the DYNAMO observations, and to improve the MJO simulation and ultimately to predict the MJO using a global model. And this slide shows the areas the MJO DYNAMO field campaign, and we're going to focus on the northern array of the soundings, and so most of the fields I'm going to show are averages over the northern array. Okay, as Wanqiu showed in his talk, there are two MJOs that was observed during the earlier part of the campaign. One is October, the other is November MJO. And we're going to focus on the October MJO. This is the 850 millibar wind anomaly and column water vapor from the ECMWF analysis. And the initiation of the October MJO is somewhere around the 15th or 16th of October. And during this time period, the ocean, the sea surface temperature is warm and to the west of the observation period of the observational domain. And so we carried out mostly the model experiments using the CAM3. The reason we use CAM3 instead of the latest version CAM5 is that CAM5 has some known issues with the MJO simulation, and also we have been doing MJO simulation using CAM3 and a revised convection scheme that we developed. And in the simulations, the MJO was quite realistic, so we decided to use this version instead of using the latest version. So in the control simulation, we used the standard CAM3 and revised the down column scheme, and then 30-day hindcast initialized with on October 6th and October 16th. For the initialized simulation on October 6th, we are about 10 days ahead of the initialization. The initiation of the MJO, and October 16th, right about the time when the MJO was initiated. So the initial condition was from the ECMWF reanalysis with DYNAMO data assimilated, and the boundary conditions we used the observed ST for the time period. So this the left panel shows the observed trim precipitation and ECMWF 850 millibar U-wind. And the next one is the CAM simulation initialized on the 6th of October. And the bottom one is initialized around the time when the MJO was initiated. And the right panel shows the propagation speed. And the way we calculate the propagation speed follows Lin et al. Basically, we sort of start from a day of a chosen day. And then we calculate the maximum precipitation along each of the lines, and then until we find the maximum precipitation over this period. And then this will be chosen as the MJO track. And that corresponds to the MJO propagation speed. In this case, for the trim data, it's roughly about 5 meter per hour. 5 meters per second, corresponding to the MJO maximum precipitation around 20th. So that's where the initiation is based on the precipitation. However, based on the Wheeler and Hendon index, which weights more on the wind field, the initiation was characterized as on the 16th. So for the MJO initiation on the forecast, which initialized on the 6th, we were able to capture the initiation of the MJO. However, the problem is that it propagates very fast, and it propagates immediately. And in fact, we have 2 MJOs immediately in it. This actually is not MJO; it's more like a Kelvin wave. And then when we initialize that right on the day when the MJO, observed MJO is initiated, again we see again we see that it propagates immediately, and then we also see 2 bands of MJO. And then this phase diagram, the black line is the observations. The red line, the red curve is based on the forecast. Initiated on the 6th, and then the blue line is the forecast initiated on the 16th. Now we are able to sort of see this track following this observed ones. However, the amplitude of the MJO is weaker compared to the observations. And in terms of model fields, we have this left panel is from the ECMWF analysis or observations, and the right is from the simulation or forecast we use for this the simulation that started on the 6th. For relative humidity, the model, the ECMWF analysis shows that it's dry at the beginning of the MJO initiation, prior to the initiation, and then it's moist throughout the troposphere after that. And then Q anomaly shows that it's very dry, about 2 grams per kilogram, drier compared to the average of the period. And then it's moist after the initiation. Temperature is a bit warmer at the beginning, and then colder, slightly colder in the lower troposphere after the initiation or after the mature state, and then slightly warmer. Now, for the wind, the observations show that we have a strong westerly prior to the initiation, and then weak westerlies in the lower troposphere, and then strong easterlies in the upper troposphere. And then by the time we get to the later stage, it becomes westerlies again, and the V wind doesn't show much of the signal here. So in terms of CAM hindcast, we are able to see this gradual moistening. However, in the prior to the initiation, the lower troposphere is a bit too much too moist, and then after that, the upper troposphere is not as moist as in observations. This is shown in the moisture anomalies field as well. This is a difference of Q from the ECMWF analysis. Again, we see that there is a moisture bias in the earlier part of the hindcast, and then dry bias later. And the temperature bias is mostly negative. That is, the troposphere is mostly cooler than observations. And the wind field is, well, this wind bias reflects the two eastward propagation of the signals. And so we're going to discuss a bit later. And then for the, if we just look at the large-scale condensational heating, convective heating, and mass flux, etc., for the part of MJO, we see that in the later part of the MJO, we have this large-scale condensational heating in the upper part and cooling in the lower part, mostly due to evaporation. And the convective heating is throughout the troposphere during the mature stage of the MJO. And prior to that, there is shallow convection. And this is clearly seen in the mass flux part. And prior to the initiation, we have shallow convection and then deep convection. And then in terms of OAR, before the initiation, OAR is higher. And by the time it gets to mostly deep convection, or after the deep convection, we get the minimum of OAR, which corresponds to the large cloud cover. So in terms of convective cloud amount, this shows actually a better evolution of this three-mode structure. Here it's a shallow convection, and then we got this type of congestors, and then gradually by the time it gets to the mature stage, and then we see a lot of deep convective clouds. So next we're going to do some experiments with nudging, and basically we're doing a number of nudging experiments. One is to nudge all the fields. When they say all the fields, so that is temperature, moisture, UNV. We nudge that towards the ECMWF reanalysis field. And then in the second set of the nudging experiments, we nudge all the fields, but except one. That is, say, in one experiment, one nudge Q, UNV, but leave in temperature unnudged. And in another, we will leave Q. And then for UNV, we put them together. Say, when we say that the one is unnudged, that means both UNV are unnudged in the experiment. And then in the third set of experiments, we nudge only one field, because these fields are nonlinear. By nudging, or by keeping one unnudged, we cannot get all the information. So this is the sort of in two extremes in this second and the third experiment. So the question is, why do we nudge the experiment? Do the nudging? So the way we do that is, say this is for say moisture experiment. Say for moisture, this is a tendency, and then this sort of dynamics and the thermodynamics, and then we added an extra term of nudging towards the analysis field. The tau is a nudging relaxation time scale. We use 1 hour, so that we choose a smaller nudging scale, so that the nudged field is very close to the reanalysis data. So for the model equation of moisture, for example, it is that moisture change is balanced by dynamics of the model and the thermodynamics of the model. In this case, physical parameterization. Physics. And then we added nudging term here. And for the observations, then we have the observed tendencies of moisture, and then we have to observe the dynamics, and then observe the physics, which is what happens in nature, although we don't have that observed. Presumably, this is what happens in nature. So if we take the difference, knowing that we have notched using very small notching time scale, the model of temperature or moisture and the observed moisture field is very close. So if we subtract this one from the other, then this is 0. And similarly, the dynamic fields are very similar. And however, the model physics is very different presumably very different from the observed model physics. And then if we take the difference, these two fields, we have notching tendency to be the difference of model physics minus, observed physics minus model physics. That is, this model physics tendency biases. Therefore, the notching tendency reflects the bias in the model parameterization. So this figure shows the notching experiment with all fields notched for the precipitation average of the northern domain of the array, the Sonian array. The black line is from the TRIM observations of the precipitation, and then the red is from the reanalysis, and the blue is from all notching fields. What I see is that the notching experiment captures TRIM's precipitation time series very well. And the reanalysis actually here in this case produces more precipitation prior to the initiation and to the mature phase of the MJO. And in the later part of the MJO, it overestimates the precipitation. So here is a Hofmüller diagram of precipitation for the observations and different sets of experiments. This is TRIM, that's 10th of October to the early beginning of November. So that shows precipitation Hofmüller from the TRIM. That's from the reanalysis compared to the TRIM. It is with the flurry. That is, the spatial scale is wider, and there is much more precipitation at the beginning of the MJO compared to the observation. This is the experiment with all fields notched. So compared to the TRIM, it captures a realistic initiation of the MJO and also the evolution of the precipitation. So the second row is for the experiments with one field unnotched. So the left one is with the humidity unnotched, and everything else is notched. So compared to this, looks like that the humidity, leaving humidity unnotched, does not affect the simulation much. And then in the next one, we have temperature unnotched. It's slightly stronger than the one with the humidity unnotched. And then the third one is with no temperature, no velocity notching. In this case, we have a little bit of difficulty initiating the MJO, but afterwards, it is doing a reasonable job. So the third row here is with only one field notched. So the left one is with humidity notched here. So we see a lot of precipitation. So this is the strongest MJO simulation among all the sets of experiments. And then the second one is with temperature notched only. Everything else is freewheeling. And what do we see that the MJO simulation is very weak, and the precipitation occurs more spontaneous. And then the third one is with velocity notching only, and keeping both temperature and humidity unnotched. In this case, it's as good as these rest of the experiments, and then as with all fields notched. So the point here is that notching velocity appears to be most effective in terms of getting the MJO simulation. And this is a field with the hidden diabatic hidden profile, and I want to point out these specific, particularly two. One is yellow, that is no humidity field is not, as we see, that corresponds to the strongest MGO precipitation. The other is no temperature field is not, and then that corresponds to the weakest MGO simulation. The rest are about the same compared to the all fields, and so they sort of scatter. I mean, they cluster around this same profiles. So we look at the nudging with all fields nudging. Then we look at the temperature tendency biases. As I mentioned earlier, the tendency biases reflect the model physics bias. In this case, for temperature, we have quarter tendency bias at the beginning, and then the quarter bias propagates to the upper troposphere, and then we have a warm bias. This corresponds to the moisture tendency biases. That is, we have heating bias in the this Q bias, yeah. We have more moisture bias here in the upper troposphere, and then dry bias in the lower troposphere. This appears to correspond to too little condensation in the upper troposphere, and then too little evaporation. That reflects the stratiform problems with stratiform cloud. And then in terms of U tendency bias, which reflects the zonal momentum transport, I have this observed U field here. And in the later part of the MGO, we have strong westerly in the lower troposphere and strong easterly in the upper troposphere. But then we have this strong westerly tendency bias. That indicates that we have too much vertical momentum transport by convection. The lowest panel shows the convective heating indicating where convection is. So we have the strongest convection here corresponding to strong vertical transport momentum. And then these panels are for, the left panel is for no moisture, no humidity nudging, and then the right is for humidity nudging only. So I put these two panels together so you can have an idea of the importance of humidity field in terms of nudging. So without nudging humidity, the structure of temperature anomaly, tendency bias is about the same. We have a cooling bias in the troposphere corresponding to the before the MGO initiation. But then in the later part, we have quarter bias. But then here, warm bias becomes more apparent compared to the experiment with nudging all fields. And then because we nudge humidity, we don't have the tendency biases, but we do have the humidity bias, humidity field itself. Looks like we have left more moisture when we nudge the humidity field. When we leave the humidity fields unnudged. And otherwise, it is comparable to nudging all fields. But then if we don't nudge humidity field and then nudge everything else, what happens is that the tendency bias for moisture seems to be larger and negative. That is, we have too much drying in this case, which corresponds to too strong convection, as we saw earlier. And this is the convective tendency, or that is diabatic heating. So we have a lot of heating here. And then because we have strong heating, the momentum transported by convection is also stronger compared to earlier experiments. And then this is for no temperature by nudging versus temperature nudging only. And for no temperature nudging, we see that the field, the biases, except that we have two chord troposphere, the tendency bias in terms for moisture actually is reasonable. It's smaller. And however, when we have temperature bias only, then we have very weak convection during the period of mature phase of MJO, but we have a lot of convection at the beginning or prior to the MJO initiation. The moisture field bias in this case actually is smallest among all the experiments. So we looked at the moist static energy budget and see if we can find some hint as to the differences among different experiments. So this is moist static energy averaged over the troposphere from 900 millibar to 100 millibar. So this advection term, it includes both vertical and horizontal advection, and that's convection, and then due to large-scale heat and diffusion, and due to radiation, and then this is not in term. These are all the experiments we have. We have 7 experiments, and this top panel corresponds to the initiation stage, and then mature stage, and the bottom one is for the decay stage. So this is a quite busy figure. So I'm only looking at a few selected experiments in the next slide.
Hey, Guang?
Yes.
This is Hunter. I just wanted to make sure we had some time for questions. So if there's a way to wrap up in the next couple of minutes, that would be great.
Yeah. This is a last slide before the conclusion.
Oh, great. Thank you.
Yeah. Okay. So remember that the humidity only produces too much convection, and then this is too little convection, and then this decay state. So for if we compare, this is over nudging, that is every field are nudged. This is initiation, that's mature, and then that's decay phase. What I noticed is that this blue corresponds to the vertical advection, and the alpha corresponds to horizontal advection. So in the mature and the decay stage, the vertical advection appears to be the large contribution to the budget. And during the initiation stage, the radiation seems to be the large term. And in this experiment, the nudging field seems important throughout this evolution. But then for the other experiments, in this case, for instance, we have the strongest convection. Then this vertical advection appears to be important. So because of the time, I'm going to wrap it up here. But then I want to make a point is that the point I want to make is that the horizontal advection of moisture, of the moisture static energy, does seem to be important in some of the experiments, and during particularly in this mature and decay phase. So the summary, the initiation of the October MJO is well captured by the model. However, the propagation is too fast. The nudging experiment shows that the nudging of the wind field, nudging the wind field, getting the wind field right is the most important in October MJO for Heineken. And in previous studies, people have mentioned that have focused on the moisture field. We note that the wind field is probably even more important. So when temperature, moisture, and the humidity and the wind fields are all nudged in the decay phase of the MJO, there's too little condensation in the upper troposphere and too little evaporation in the lower troposphere, indicative of too little stratiform cloud particles. And then finally, there's too much downgrade in the vertical transport of momentum, and because in this case the parameterization of convective momentum transport is largely downgraded. So this may reflect the fact that we are not able to capture upgrade in the transport of momentum in some of the convective episodes. So we're looking into that. Thank you.
Great. Thanks so much, Guang. That was great. Why don't we dive right into the questions, because I know we have a few of them, and I want to try to get them all in. I'll start out with one for the first presentation for Wanqiu. The question is from Marcella Ulate. I'm hoping I'm getting that kind of right, the last name. And the question is, do you get the same results for precipitation on slides 22 and 23, where you showed the improvements of OLR forecast with the different cumulus schemes and the climate versus TMI SSTs?
I didn't look at the comparative precipitation, and but we do just look at the rough relationship between OIR and precipitation, and they correspond each other very nicely. So we believe the precipitation is also very good. I mean, when the OIR is good. Thank you. Does that answer the question?
Well, we'll see if they write in a follow-up, but for now, yes, it does. All right. Great. That was quick. Thank you. Okay. The next question is also for you, and it's from Pallav Ray. And that question is, he says, I thought in general, many models show faster propagation than the observation. Why did the GFS CFS model have slower propagation?
Actually, it's always a confusing thing to me too. Some people, I mean, we always say the model MGO is too fast. Then now some people say the model, MGO propagation is too slow in the model. But actually, I think it depends on what models to look at. If you look at the earlier in earlier years, when we look at the MGO in atmospheric model only, the MGO propagate too fast. But if you look at the couple model, the MGO tends to be more stationary or towards the slower side. So it's still it depends on what kind of model to look at. Probably the coupling is probably slowed down the MGO propagation. That's my guess, but I need to look at more details. If you look at the semi-perons, there are a couple of papers on semi-perons, semi-5, semi-3. Most couple models are too slow. If you look at couple model, yeah. Thanks.
All right, thank you. And the final question is for Guang Zhang. It's also from Pallav Ray, and the question is, what was the nudging timescale and why?
The nudging timescale, as I mentioned earlier, it's 1 hour, and we tested the different timescale. We use 3 hours, 6 hours, etc. And the reason we use 1 hour is try to make sure that the model fields are close to the reanalysis fields, as that way we'll see that the nudging tendencies would reflect closely to the model physics biases. However, if we use a longer nudging time scale, then the model fields differ a bit more from the observations. Therefore, that nudging tendencies would not only include the model physics biases, but also reflect some of the differences in the dynamics field.
Great, thank you. We'd like to thank everybody for joining us. We'll wrap up the presentations at this point. So thanks everyone for joining us, and also thank you to today's presenters, and thank you to Amrit here at the CPO for helping us, for helping the presenters get prepared and for helping with the technology. Please join us again in 3 weeks on Wednesday, August 13th at 2 p.m. for the next set of presentations. Toshiaki Shinoda of Texas A&M Corpus Christi will present on upper ocean processes associated with the Madden-Julian Oscillation in the Indian Ocean. And Eric Maloney of Colorado State University will have a presentation on understanding MJO dynamics and model bias in DYNAMO hindcasts. Thanks again and have a great day.
Thank you.
Bye-bye.